Hi guys, welcome back to a new video. Today we'll be going over related rates, the concepts behind them. Really, related rates isn't one thing that I can give you an equation, was okay, so this is how you use the equation, and then we're done. It's more of intuitive thinking and more how are you going to visualize this in your head and paying close attention to what you're given, what you can find, what you know you don't know, and what you don't know you don't know. Less of that last one though. And so, without further ado, let's just jump right into it. Okay, so we're given a diagram and a question right here. So we're given the dimensions of looks like a cone tank of water. The tank of water shown is being filled with water at a rate of 12 meters cubed per second. At what rate is the depth of the tank changing when r is equal to 10 meters? So, first thing you want to do in questions like these is, okay, so you're getting values. What do they mean? In a calculus standpoint, how can you write them out? And so when I look at this question, I see a rate of 12 meters cubed, 12 meters cubed per second. Okay, that means it's going to be derivative in terms of time because it's going to be a per second and it's going to be a rate of change, right? So, okay. But it says that the tank is being filled with water, and this is meters cubed as opposed to meters squared or meters. So I can infer that this would be a change in volume. Let's go to 12 meters cubed per second. The main thing to avoid here, pretty big mistake to avoid, is what if it was being drained, not filled? Then this would be negative, and it would ultimately change your final result. But right now, we don't have to worry about that. Okay, so what else do we know? Well, we know that the radius could be 10 at a point in time at which we're evaluating, so we could set r equal to 10. Okay. And probably the most crucial rule of this step is, what are we looking for? What is this question asking? Okay, so at what rate is the depth of the tank changing at this certain time, basically? So we're looking at the depth change. If we name the depth h, we could just represent this as a dh dt. And really writing them out in a sort of calculus notation where you can see them visually and express them through math is the best way. You can really write them out so you can really visualize what equation we're going to use to take a time derivative of, essentially, because it's going to be related to this. So we want to find a relationship between dvdt and dht. And writing out these variables out this way is really going to help you find which equations you're going to be looking for. Okay, so we have volume, the radius, and the height. Okay, so we can look at, let's say, probably could be the volume of a cone, because we're looking at volume, radius, height, as I said before. So the volume of a cone can be written as velocity. Volume is equal to 1 over 3 pi r squared times h. Okay. What if we just take the time derivative right off the get-go? Maybe we have all the variables, right? So dv dt is equal to 1/3 pi. Now this is where it gets tricky, because 1/3 pi we were able to avoid because they were both constants, and thus the derivative, since they were attached to a certain variable here, then it wouldn't have changed. But we also have to see at r as a variable, right? Because as the time is changing, r is also going to be changing in this equation, in this problem. So we can't just assume that dr dt is going to be 1, because it's not shown here. But we don't know that dr dt is equal to 0, because once again, we're not told, and we know that the radius is going to change depending on the level of the water, because it's a cone. So what do? We know that r is a variable, so we have to take a product rule. So we're given 2r, take the derivative of r first, dr dt through chain rule, plus r squared dh dt. Okay, now I'm going to be honest with you guys, this equation is useless to us. We know r, sure. Oh, sorry, there should be an h right here. But we don't know what DRDT is. As I said before, there's no way of finding what DRDT is with the information that we have. So we can't use this right now. Okay, so what can we do? Well, what if we only have one variable here, not two variables? Like, what if we found R in terms of H or H in terms of R? Oh, this is when you start thinking, okay, so we're looking for what DHDT is. And so if this was just volume in terms of height, let's say, we can easily take the time derivative of both sides and see, okay, so then we would have a dV dt here, and eventually we would only have a DHDT here. So that's probably how we're going to do it, right? But the trick is, how are we going to find R in terms of H? Well, if we go back to our diagram here, if you just label this as R and this is H, we can set up a proportional triangles, right? So, oh, that is a terrible triangle. Let's pretend this is a right angle. So, geometry tells us that we could look at this part as proportional, right? So if you write this as R and this small part right here is H, this whole thing is A, and this length right here could be 26. Okay, and we can set up the ratio. So R is to H as 26 is to 8. And from here, we can find what R is in terms of H. R is equal to 26, or 13 over 4, if you want to simplify it, H. Okay, so if we take this and we put it into our equation, we're getting somewhere, right? So we know that volume is equal to 1/3 pi R squared. So we're going to take this term and square it, 169 over 16, and then H squared times H is H cubed. Okay, let's keep going through the equation. Let's say the time derivative and see what happens. So we have dV dt is equal to our constants again, 1/3 pi 16, and then 3h squared dh dt. Now this 1/3 and this 3 cancels out, so I'm just going to erase that. Rewrite this as h squared. And just take away this 1/3. Well, we're in a slightly better position than we were last time, because now we have one unknown variable right here, which is h. But through this method as well, we can find what h is. So if you set up a similar triangle right here, proportion, and we just set r equal to 10, we only have one unknown variable. Therefore, then when you set up the proportion right here, 10 over h is equal to 26 over 8. We have h is equal to 40 over 13, I believe. Yes. Okay, so now we know what h is. If you just plug in all our knowns, we can find our unknown, and that is there is a solution to our problem. So 12 is equal to dV dt, pi 1 over 16. Okay, we plug this in basically. 40 over 13 squared dh dt. Now at this point it just becomes plug this into your calculator and find an answer. But I will spare you and me the troubles of plugging this into our calculator and just give the answer. And also always include the units. And there we have our answer. Now, actually I boxed this preemptively because we have to check, make sure that everything lines up. And so this is the part that, if we were as an exam, this is the part where I'll be looking at, okay, did I do my math right? Did I make any unclear assumptions? Let's clear that up. So I go through this, read the question again. Okay, volume, okay. My diagram here makes sense. There's a ratio between like triangles. I also have my ratio, R over H is equal to 26 over 8. And that does make sense. Okay. So everything seems to be working. I used all my variables that they gave me. That's always a good sign, because if you don't use a variable, chances are you're missing some part of it, or you made a shortcut. And so then I ask, then the most important step in this whole verification process is, at what rate is the depth of the thing changing? That is, we wrote this as DHET. Height is changing over time. That is what we're being asked, so therefore I can box DHDT. And we never forget our units. We're given meters per second, meters cubed per second, so we give back in meters per second. And there is our answer. Now, this related rates problem is going to be one of the harder ones that you're probably going to encounter in either AB or BC or 1 and 2 calc. But because the main part that is hard right here is finding that there's the drdt that we can't find, and so we have to substitute r in terms of h into the problem. But other than that, it's relatively looking at just conceptualizing what can we look at, what assumptions can we draw from what we were given. Always write out your variables first, and then from there look at your equation. What can you deduce from your equation? I found, okay, so I can't find what drdt is. In that case, I was like, okay, so that doesn't work. I gotta find another way to use r in terms of h, or vice versa. Okay, so I'm looking for volume, I'm looking for dHdt. So I'm gonna represent r in terms of h, and I have an equation in terms of volume and h. I did that. I used my diagram. It worked through with this, found what r is in terms of h, plugged it in, and just from there it's just simple algebra. I hope this was useful. This was, once again, just to build up conceptual understanding and really how to approach these problems. I hope it was useful, and I hope you enjoyed. Thanks for watching.